This video begins to address the standard of finding the zeros of polynomials. Now before we can talk about that explicitly, we have to build up some skills that we're going to need in order to be able to find the zeros of polynomials. So right at first here, the focus is going to be on dividing polynomials. And to begin our thinking about it, let's think about taking the improper fraction 45 over 7 and turning it into a mixed number. All right, so the answer is 6 3/7, and remember that the way you do that is you take the top divided by the bottom. And we realize 7 goes into 45 6 times. And there's 3 left over out of 7, so the answer is 6 3/7, which is the same thing as saying 6 plus 3/7. Also, an alternative way of kind of conveying the same information is to say that the number 45 can be made by taking 7 times 6 plus 3, or in other words, the divisor times the quotient plus the remainder. And in both this statement and this statement here, linking this up with 6 plus 3/7, we kind of see two ways we can express the same idea with polynomials. So let's start with the second one down here. This one, if I have a polynomial and I divide it by some other expression, then I can say that's equal to my quotient plus a remainder over the divisor, just like my quotient of 6 plus the remainder of 3 over 7. I can also think of it like this as well, that any polynomial can be written as the divisor times the quotient plus the remainder. All right, and so we'll use these ideas as we go along. But first, let's just really focus on how do we go about dividing polynomials. So to start off with, we set it up just like any other long division problem, where I put the dividend, right, the thing that I'm going to be dividing, inside, and I put the divisor, the thing I'm dividing by, on the outside. And to kind of help us think through this whole idea here, let me just go ahead and do a little division problem on the side here. How about 939 divided by 7? All right, so 939 divided by 7, if I was to start this, I would try to put 7 into 9, right? So I'm kind of ignoring the 39 part and just saying, how many times does 7 fit into this 9, which of course would be once. And then I'll take 1 times 7, put that down there, and then subtract those and see what the remainder is. Okay, so we'll pause this here and go over to our actual problem. So similarly to how I ignored these two, I'm going to ignore my 6x and my 72 for a second, just focus on the first term. And I'm going to ask myself, how many times does x fit into 6x squared? Or maybe to put it a better way, what do I multiply x by to make 6x squared? Well, the answer isn't too difficult. I would multiply by 6x. So I'm going to put 6x above the x term here. And then just like I multiplied my 1 and my 7 and put it below the 9, I'm going to multiply 6x and x plus 5 and put the results below these terms here. So 6x times x is 6x squared. 6x times 5 is 30x. And then lastly, what did we do with our 7? We subtracted it from 9. So we are going to subtract these terms that were the result of multiplication from the original polynomial. So of course 6x squared minus itself is 0, so I won't even bother to write anything. And then we have to be careful. This minus sign does distribute through to both terms. So I'm really taking negative 6x minus 30x, so that gives me negative 36x as my remainder. All right, so now if I go back to our numerical problem, I would drop the 3 next, And I would say 7 fits into 23 3 times. 3 times 7 is 21 with a remainder of 2. Okay, and then I just keep repeating the process, right? Drop the 9, 7 fits into 29 4 times. 4 times 7 is 28. Minus 1, or minus 28 is 1. And so this gives me an answer of 134 and 1/7, right? It gives me the same thing as taking 134 over 7, or 134 divided, or excuse me, not 134, 939 divided by 7. So over here, just like we dropped a digit after we were done subtracting, we are going to drop this last term. And then I ask myself the same question as before with the 6x squared. Now I'm saying, what do I multiply x by to make negative 36x? Well, the answer would be negative 36. So I multiply through. Negative 36 times x is negative 36x. And then negative 36 times 5 is negative 180. But I'm going to subtract that off. So if I have negative 36x minus negative 36x, it's really negative plus a positive, so that's again 0. And negative 72 minus negative 180 is the same as negative 72 plus 180, and so this is going to give me 108. So my answer here is 6x minus 36 plus 108 divided by x plus 5. So what we're saying is that 6x squared minus 6x minus 72 divided by x plus 5 is equal to this. All right, now we're going to do another problem here, but we're going to, in the midst of it, discover a shortcut. So we're actually going to do this two ways. We're going to do the long division way, as in the previous example, and then I'm going to show something called synthetic division, which is kind of a shorthand way of doing the problem. So let's start it the normal way. So we've got 3x to the fourth minus 2x squared plus x minus 1. Now one thing I want you to notice is that there's a cube term missing, right? There's no x to the third power. So anytime you notice one missing, it's important to put a placeholder in. So I'm going to put 3x to the fourth, but I'm not going to jump straight to my next term. I'm now going to put plus 0x cubed. Then I'll move on to my x squared term and my x term and my constant term. And then I'll put x minus 1 on the outside. All right, so we'll go through the process here. What times x equals 3x to the fourth? Well, that would have to be 3x cubed. Multiply that through, we get 3x to the fourth, and then 3x cubed times negative 1 is minus 3x cubed. And you can see why I wanted a placeholder there, right? I want to be able to line up like terms, and so I wouldn't have been able to do that if I didn't have a cubed 0x cubed term right here. So get 0, of course, here. 0 minus negative 3x cubed is positive 3x cubed. Drop the minus 2x squared. And we can see to make 3x cubed, I would need to multiply x by positive 3x squared. And then multiplying x and negative 1 by 3x squared, we get that. And we subtract both terms, which gives me 0 in the x cubed and then positive 1x squared. And drop the x. X times 1x would give me x squared. x times negative 1 gives me negative x, and x minus negative x is x plus x, so that's 2x. Drop that down for minus 1, and then we know that we got to multiply by 2 to finish this thing out. So 2x minus 2. I'm almost out of room on the bottom here, but I get a remainder of 1. So all of that gives me, write the answer over here, 3x cubed plus 3x squared plus x plus 2 plus 1 over x minus 1. And that's the answer we get when we divide that big polynomial by x minus 1. Box that up there. Okay, so what about this shortcut? The thing I want us to notice is that, first of all, if I could just put things in the right place, right? And if I could just know where x cubes go and x to the fourths and all that go, then I really don't need to continue to write all these variables raised to powers, okay? So because I have x cubes always in this column, x squared's always in this column, x is in this column, right? They're always all lined up. So if I could just remember what to put in what column, I can save myself a lot of writing if I do that. And then the other thing I want us to notice is that the remainders always come from the product of the result and the constant number that we're dividing by. Okay, so that's what's always producing the remainder. Okay, so right, just kind of looking at this, right, and then looking at this one that produces this remainder, right? So it's always kind of coming from this 1 here. So what we're going to do with synthetic division is we're going to start by kind of doing an upside down division sign, if you want to look at it that way. And the first thing I'm going to do is in here, I'm going to put all of the coefficients for the original. So I'm going to put a 3 for 3x to the fourth. I'm going to also remember my placeholder here, so I'm going to put a 0 for 0x cubed, a minus 2 for x squared, negative 2x squared, a 1 for x, and a minus 1 for the constant. So that's the first step. Then on the outside here, I'm just going to put the 1. Again, understanding that remainders always just came from really this 1 and not the x. So I'm just putting the 1, and then I'm going to put another line a little bit further down, but with a gap between here and here. So the first thing that I'm going to do is I'm going to drop this 3 to this spot. Okay? And the act of dropping that 3 to that spot is the realization that if I just have a 1x out here, then whatever coefficient is in the leading term is the one that I'm going to put in my answer. So that's the idea of dropping. So down here is where the answer is going to be produced from. And then I know that I take that coefficient times the 1 to make this number. So 1 times 3, and then I'm going to put the 1 times 3 right there. So multiply that by that to make that. Now, the only thing is I had a minus in front of my 1, right, producing this minus sign, but then I subtracted. But we know that subtracting the negative ends up just plusing the positive. So in synthetic division, we actually just simply add these two. So we just add 0 and 3 and put the result here. Okay. Now I'm essentially at this stage of the long division process. And so once again, I'm going to multiply my 3 and my 1. So that's going to be multiply this 1 and this 3 and put it there. And I'm going to again add, and there's a 1, and there that 1 goes with this 1 in front of the x squared. And then 1 times 1 is 1, which I'll put there. If I add those, I get a 2, and that's this 2 right here. And then I multiply 1 and 2 and put that there. And then the last part is I do one last subtraction to get the remainder. And so to remind myself that this last one's the remainder, I kind of box it off, add those, and I get 1, which is the remainder I got. And so the way all this translates out is we understand that if we started off with something that was x to the 4th, and I divided by something with an x, my leading term in my result should be x cubed. So this is going to be 3x cubed plus 3x squared plus x plus 2 plus 1 divided by x minus 1. And so you can see we get the same answer that we had here, but much quicker. So the thing I want to emphasize just real quick before we move on is that synthetic division is used when the divisor has the form x minus c. Okay? If it is more complicated than this, then you cannot directly use synthetic division. And also note that if you have x plus a number, then you would put the negative of that number outside here. So we run into that in this problem. So let's use synthetic division to divide these. So first of all, we look for any missing terms, so we make sure we do placeholders. So I have 2x cubed, 9x squared. There is no x term, so I put a 0, and then minus 5. And then on the outside here, right, x plus 3, it's got to be in the form x minus a number. So this is x minus negative 3, and so we put a negative 3 on the outside. And then we start the process. Drop the 2, multiply to make negative 6, add to make 3, multiply to make negative 9, add to make negative 9, multiply to make 27, add to make 22, and this last one is a remainder. So this tells us that, and see how quick this was, 2x cubed plus 9x squared minus 5 divided by x plus 3 is equal to 2x squared, that's coming from this 2, plus 3x, coming from the 3, minus 9, plus a remainder of 22 out of x plus 3. Right? But if we have the proper form for what we're dividing, this synthetic division becomes really nice. So how do we use this idea of synthetic division to help us find zeros of polynomials? Okay, well the answer to that is in this factor theorem. It says that a number is a zero of a polynomial if and only if x minus that number is a factor of the polynomial. So in other words, by factor what we mean is that I could take my polynomial and I could say that it's equal to x minus c times something else. And the something else doesn't matter too much, but the idea is if you just look at this and then you plug a 0 in for p of x, then x minus c would have to yield information about a 0. In fact, you would set it equal to 0 and you would find that x equals c must be a 0. Okay? So if we can just show that something is a factor of a polynomial, then we've shown that the corresponding number would be a 0. Okay, so let's look at example 5. It says show that x plus 2 is a factor of the polynomial, which would mean that x equals negative 2 is a 0. Okay, so how are we going to show it's a factor? Well, remember, something's a factor if when you divide by it, you don't get a remainder, right? So we know that, 45, 9 is a factor of 45, right? Because 9 goes into 45 5 times, and the remainder is 0. So if we can just use synthetic division and show that when you do divide this polynomial by x plus 2 that you get a remainder of 0, that shows it's a factor. All right, and then when we've done that, we'll go ahead and find the other zeros of the polynomial as well. So with synthetic division, right, we're looking out for those missing terms. So we have an x cubed term with a coefficient of 1. We're missing our x squared term, so we put a 0, then -7, -6. And then it's x plus 2, so we're going to put -2 on the outside and begin our synthetic division. So we drop the 1, -2 times 1 is -2, add 0 and -2, then multiply to make +4, add those to make -3, and then we get +6, and that's good because adding those gives us a remainder of 0. So here's what this shows us. It shows us that our polynomial p of x, which started out as x cubed minus 7x minus 6, is equal to x plus 2 times, and we can put the result here as well, x squared minus 2x minus 3. So from right there we can see that x equals -2 is a 0. Right? Because if we put a 0 here, the zero factor theorem says that any factors can produce a 0. Now this one, we can go ahead and factor further. In fact, it's just that we'll just use our typical factoring of quadratics here. So no synthetic division necessary. So x plus 2, and then we can see that that's going to break into x minus 3 and x plus 1. So what we can see is from this, x equals 3 and x equals -1 are also zeros. Now what I want to caution you on here is that all this business of the synthetic division, it's all really nice and convenient, but it's only valid when you are dividing by something of this form, right? Of x plus or minus a number. So in this next example, I just want to illustrate the point that if they are giving you something more complex, you cannot use synthetic division. You have to go back to polynomial long division. So because you will see some instances of more complicated long division like this, let's go ahead and run through one example. So here, as I'm writing out this first one, there's a lot of terms, but at least there's no missing terms, so I don't have to worry about putting in those placeholders, right? Putting in a 0 for a particular type of term. And then this time I'm dividing by a quadratic. But when we see this, we don't have to panic here. We just essentially follow the same procedure that we did before. So we're going to look at the leading term only in both of them. And I'm just going to say, what do I multiply 2x squared by to make 4x to the 5th? The answer would be 2x cubed. So I'd put 2x cubed up here, and then I multiply 2x cubed by all three of these terms. So that's 4x to the 5th plus 6x to the 4th minus 2x cubed. And then we are subtracting that. Sorry. So 12 minus 6 gives 6x to the 4th. 3 minus -2 is 3 plus 2, so that's plus 5x cubed. And then we drop down that next term. So we multiply 2x squared by 3x squared in order to make 6x to the 4th. And again, multiplying through 3x squared by each term, 6x to the 4th plus 9x cubed minus 3x squared. So 5 minus 9 is -4, and then -7 plus 3 is -4x squared. Drop down the 5x. So you can see this all works in just the same way as when it was a little simpler. We just have to kind of be a little more patient with it, be a little more careful. So multiply negative 2x by each of those terms. So we'll be left with 2x squared plus 3x, and then this will be the last one, minus 1. So we just multiply by 1 in this last instance, so 2x squared plus 3x minus 1. And so notice what's happening here is we end up with a nice 0 remainder. So the answer to this division problem is just 2x cubed plus 3x squared minus 2x plus 1. No remainder necessary. So the last little topic here is to talk about how do we find the zeros of polynomials if we really have no information given to us. Right? Back in example 5, we did learn how to take a number and prove that it was a 0, but we didn't talk about how do we go and find those zeros ourselves. Now there's all sorts of interesting algebraic ways that you can use, basically some really cool algebraic theory that will lead you to those answers, but for us we're just going to rely on technology. So we're first going to take the graph of our equation and find zeros on the graph and basically go until we find a nice 0, what we call a rational 0, which is a 0 that is either an integer, it could be written as a fraction. So we're going to find one of those first. Then we'll perform synthetic division on that particular 0 or that factor in order to be able to factor the polynomial further. And then once we do that factoring, whatever's left, right, that quotient, we'll then take a look at that new polynomial and basically repeat the process. And we repeat that process until the quotient is a quadratic, and then we can use the quadratic formula or other techniques to get the remaining zeros. So let's find all the zeros for the polynomial given to us in this example. So like we said, we're just going to start in our calculator, go to our y equals menu and type this function in. And I'm just going to go to Zoom standard, so I'm looking at the standard window. Alright, and so I can see my polynomial. I can't see all of it, but here's the point. I'm looking for zeros, right? So as I'm looking at this, this one here is crossing not on a nice tick mark. Now it might be still a pretty nice 0. It might be like 1/2 or something like that. But I'm going to probably start by looking at one of these two zeros because it looks like they may be crossing right at a tick mark, which would mean they're an integer value. So we'll go to calc, right, the second function of the trace button, go down to 0. And this is a lot like finding your max and your mins that we did earlier in the quarter. So you're going to get left of your 0. You're going to get to the right of your 0 for right bound, and then you're going to give it a guess somewhere in there. And so sure enough, it says x is equal to -2. So we can just jot that down first. We can say that x equals -2 is a 0. But understand what that means is that so x plus 2 is a factor. So we already know that the polynomial can now be written as x plus 2 times something, right? I don't know what that something is yet, but times something. So in order to find that something, that's where synthetic division comes in, right? Where we divide this polynomial by x plus 2 and see what's left over. So over here, let's do that. So I'll put a -2 on the outside. and then put a 2, a -1, a -13, and a -6. And of course it'll all shake out this way as long as we haven't made any errors, but let's just understand what we should be expecting is right here in this box should be a 0, right? And if that's not the case, then something's wrong, because anytime you've got a 0, when you divide by its factor, you should get a 0 remainder, otherwise it's not a 0. Put our 2 down here, so that's -4, -5, -2 times -5 is +10, and then -2 times -3 is +6, and sure enough, you add those, you get 0. But then here's a real important piece of information. This tells me that what's left over is 2x squared minus 5x minus 3, so that's what goes in here. All right, now this is a quadratic. So at this point, I don't really need the graphing calculator anymore. I could go try to find another 0, but I've got a quadratic, and once you have a quadratic, you're just going to use the quadratic formula to get your other zeros. So let's do that. So just based off of this part, I'm now ignoring x plus 2. I'm going to say -b, so the opposite of -5, plus or minus the square root of b squared minus 4 times a times c. Make that square root extend out there. All divided by 2a, so 2 times 2. So that's going to be 5 plus or minus. So inside that square root there, we've got 25 plus 24, which is 49, divided by 4, which is equal to 5 plus or minus 7 over 4, which on the one hand is 12 over 4 if you use the plus, which is 3, or on the other hand is -2 over 4, which is -1/2. And so what we can do here is we can find all these zeros and list them all in one place. So x equals -2, 3, and -1/2. Those are all of our zeros. And furthermore, I can actually write this polynomial completely factored too, because it does say factor and find all zeros in the question. So we can say p of x equals x plus 2, right? We know that from over here. And then times, we need this 2x squared minus 5x minus 3 to factor in such a way that it yields 3 and -1/2 is zeros. And since there's a leading term of 2x squared, we know that we're going to have a 2x here and an x here to make that 2x squared leading term in the quadratic. And then I can make my 0 of -1/2 by putting a +1, and make my 0 of 3 by putting -3. So there's my zeros and my completely factored polynomial.